This video is about the domain of an algebraic expression. We'll start some notes with a definition, which is this. The domain of an algebraic expression is the set of all real numbers which can be substituted into the variables of the expression to produce real number results. For now, this list will grow, but for now we determine such domains as all real numbers except, so we're simply going to exclude some. We're going to exclude those which cause the following two problems. First, division by zero, which is undefined, and secondly, even roots of negative numbers. Let's consider an example where we want to find the domain of an expression. This first expression is 1 over the square root of x minus 1. To find the domain of this expression, we'll consider our definition, which has those two main parts. The first part being that we cannot divide by 0. And our second part being that we can have no even roots of negatives. And so considering only these two possible problems, we want to make our domain all real numbers except any which would cause these. Let's take a look at them one at a time. First of all, might we be in danger of dividing by 0 in this given expression? Well, sure. It's a fraction, which means if its denominator is 0, we have a problem. Let's consider when the denominator might be 0 by setting it equal to 0. We'll take the expression square root of x minus 1, which is the denominator, and set it equal to 0, and simply solve for x. To do this, our first step could be to square both sides of the equation. This result will give us x minus 1 on the left side equals 0 on the right side. 0 squared is still 0. Then we'll add 1 to both sides to get x alone for a result of x equals 1. Now, let's think about what this all means. When x equals 1, this original equation here is true, that the square root of x minus 1 equals 0, but we don't want that to happen because that would mean we're dividing by 0. So, what this all means is that we must exclude the case when x equals 1 because it causes the first problem, dividing by 0. Secondly, let's consider the second case of no even roots of negatives. Notice there is an even root in the denominator of this expression. It is a square root, which means what's inside of it, which happens to be x minus 1, must be greater than or equal to 0. That would mean it's not negative. That's what we have to avoid. Solving this inequality, which would involve adding 1 to both sides, would leave us with x is greater than or equal to 1. This means we must have this to avoid the even root of a negative. Now, our domain has to be the final result when we put both of these considerations together. We're going to use set builder notation, which involves these curly braces. And our first example here will be the set of all x's, and then we put this vertical line meaning such that, or that we're about to describe. What we know is that these x's must exclude 1, and they have to be greater than or equal to 1, all at the same time. Well, to put those two together, this means x simply has to be greater than 1. You see, if x is greater than or equal to 1, this technically includes 1, but our first condition said we have to exclude 1. So the summary would simply be all x's such that x is greater than 1. Let's consider another example where we want to find the domain of an expression. This expression has a numerator of x squared plus 1 and a denominator of x squared minus x minus 2. Well, to consider the domain, we want to remember our two conditions. The first being cannot divide by 0, and the second being no even roots of negatives. Let's consider how these might apply to this given expression. For the first part of not dividing by 0, we'll consider that we do have a fractional or rational expression with a denominator. So we must consider carefully, might this denominator of x squared minus x minus 2, might that ever be equal to 0? Well, the only way we'll know is if we solve this as an equation. Now, this denominator happens to be a factorable polynomial, so we'll go ahead and recall a way to solve a quadratic polynomial by factoring, and the factored form of this one should be two binomials, the first one being x minus 2 and the second one being x plus 1. You might recall the zero product property, which says when we have a product equal to 0, we can set each of those factors to 0. So x minus 2 could be 0, or x plus 1 could be 0. Solving each of these equations would then yield x equals 2 or x equals negative 1. Now, recall the context here. We started this equation, or created it, by setting it equal to 0 because we must exclude when that happens, which means we must exclude these two results we got while solving the equation, 2 and negative 1. So we'll get there by the end, but that's our first part. Part A, cannot divide by 0. Part B, where we want to make sure there are no even roots of negatives, notice in this expression there are no even roots. Therefore, there's nothing to consider for that second part, which means our overall domain in set notation is all x's such that x is not equal to the two results we solved in part A, which are negative 1 and 2.